All right, so our sine function is going to come straight from this thing right here. Okay, so that curve that we were investigating yesterday, talking about the amplitude, the period, all that kind of stuff, and graphing it in GeoGebra, I want to show you where that curve comes from. Okay, and once we understand that, we'll dig back into amplitude and period and actually investigate that inside some different functions. What I want to do right now is I want to take a theta value, okay, and I'm going to do this in radians, but we could do it in degrees, but we just have to be careful with our graphing tool to make our x-axis in degrees. In degrees, if I like working on TIA 384, there's quite a bit of manipulation with the window that in the structure of the graph that we had to mess around with. Really the same thing with Desmos. So I'm going to do everything in radians. It's more natural, and your calculator is going to adjust to that easier. So what I'm going to do is I'm going to take and create a bunch of ordered pairs here. Okay, and we can think about this different ways. I can either say f of t is equal to sine of t, so I can talk about the distance along the circumference of the unit circle, or we can write it as f of theta is equal to sine of theta, which that would be interpreting now as that value there, right? But what do we know about theta and t on the unit circle? They're the same, so it doesn't matter here, okay? My input value, or my independent variable, is going to be theta, or t, okay? My dependent value is going to be that value of theta or t evaluated in the sine function, okay? Well, on the unit circle, isn't the sine function y over r? And r is 1, right? So on the unit circle, isn't sine of theta just y? So I'm going to take a theta value, for instance, let's just say 0 radians, and see then what is the y value of the ordered pair for 0 radians. The y value is 0. Does that make sense? Okay. Now I'm going to go to the next one that's convenient. It's pi over 6. So pi over 6 is the next radian measurement that I look at. That's either theta or this distance t. And what is the y value at pi over 6? 1/2, right? Okay. So what I'm plotting here on the right-hand side of this table is a theta or t value, comma, the y value from the unit circle. Okay. Now I call this the independent and dependent variable. I think that's the best way of doing it, not to get you confused with x's and y's and t's and thetas. But when we graph on the Cartesian plane, this can be our x value and this will be our y value. Does that make sense? They're ordered pairs. Then we go pi over 4 as my angle or my distance, and then the y value that is coupled with that, radical 2 over 2. I'll do pi over 3. Y value coupled with that is radical 3 over 2. And I'll do pi over 2, and the y value coupled with that is 1. Okay. Now, I can keep doing that all the way around, and I should do that all the way around. Okay. And I will create this list of about 17 ordered pairs that we could plot, right? But what you're going to find out is that these values over here, because they are the y values off the unit circle, they start repeating with symmetry, right? Okay. So I'm going to use that knowledge to help me graph this thing on GeoGebra. So I've established GeoGebra's x-axis in terms of pi over 6, which is really easy to do on GeoGebra. If we were doing this by hand, and I'll show you how we do this by hand. You remember the other day I told you when we were writing the unit circle that learning how to count to 2 by 8 and learning how to count to 2 by 12 is going to be important? It's because when we graph it on the sine curve and the cosine curve on an x and y axis like this, here is essentially 2, And I've counted there by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 intervals. Does that make sense? Okay. So we basically what we look at here, that x-axis is the unit circles in regards to distance, those t values, cut and laid out straight on the x-axis. Is that okay with everybody? Okay. So obviously we still refer to this as the x-axis, but we could do some relabeling if we wanted to. Okay, we can call this either the t-axis or the theta axis. Okay, or we can leave it as the x-axis. But if I use this as the t-axis, then this is going to be, the y value would be f of t, which is sine of t. Okay, or if I use theta, this would be y equals f of theta, or equal to sine of theta. And if I left it as x, we would establish that this is y equals f of x, or the sine of x. Does that make sense? Okay, so just a redefinition of your variable doesn't really matter too much. You'll see all of those being used. But if I graph these points, 0, 0, okay, and then we had pi over 6, 1/2. Then we had pi over 4, square root of 2 over 2. And then we had pi over 3, square root of 3 over 2. And we had pi over 2, 1. Okay, so those blue points are the points that I had written right there. Okay, everybody? Now I'm going to do the same thing, but I'm going to use this quadrant. Okay, and because of symmetry, I should know that this point right here is going to be symmetric to another point over here. Does that make sense? Okay, so at 2 pi over 3, I should have the same y value as I had at pi over 3. And that was the square root of 3 over 2. Okay. At 3 pi over 4, I should have the same y value that I had at pi over 4. Square root of 2 over 2. At 5 pi over 6, I should have the same y value I had at pi over 6. And at pi, I should have the same y value I had at 0. And I get those. Okay. So these points here, those red points, are the second quadrant ordered pairs, theta, the y value. It's okay? Then we're going to the third quadrant. Third quadrant, first angle I come across is 7 pi over 6. It should have the same y value as 5 pi over 6 had, or that pi over 6 had, but it should be negative. So negative 1/2. 5 pi over 4 should have the same y value as 3 pi over 4, or the same y value as pi over 4, but it should be negative. Okay, and then at 4 pi over 3, same as pi over 3, but negative. And then at 3 pi over 2, we should be at negative 1. And those are the ordered pairs from the third quadrant. Now, as I go to the fourth quadrant, are the fourth quadrant ordered pairs the same as these? Okay, the y value is the same, right? Okay. And the first point in the fourth quadrant, you have the y value the same as what point L was. So when I go 5 pi over 3, should be negative square root of 3 over 2. When we go 7 pi over 4, should be negative square root of 2 over 2. And we go 11 pi over 6, should be negative 1/2. And then 2 pi, 0. And those are your fourth quadrant points. Does that look like a smooth sine function? Like we said yesterday, if I look at, I'm going to say if we're looking between 0, and 2 pi, the sine function looks like that, right? Okay. Now, of those 17 points that are there. I think there's 17. Some of them are really easy to plot. Some of them are really hard to plot. Okay. Think about this. If I'm working on the parent function for the quadratic, y equals x squared. Plotting 0, 0, 1, 1, 2, 4, 3, 9, right? Negative 1, 1, negative 2, 4, negative 3, 9. Those are the parent function points that we've talked about in the past. Can I plot 1/4, comma 1/16? Is that an ordered pair on x squared? Is 1/2, comma 1/4 an ordered pair on x squared? Right? Okay. Is 2.5, comma 6.25 an ordered pair on x squared? They are. Are those points kind of hard to graph? Got to do a lot of estimation, right? Well, radical 3/2 is 0.866. If I ask you to graph 0.866 on a y-axis, that's hard to do. Radical 2/2 is 0.707. That's hard to graph. Okay? So there are some points on here that are not very convenient for us. Okay? But would you all agree that point A, point I, and point Q are really easy points to graph? They got y values of 0, right? They've also got really nice theta values, t values, or if you want to refer to them as x values, or the independent variable, okay, along the horizontal axes. How do these three relate to each other? How does this one relate to A and Q? It's the midpoint of A and Q, okay? So if I can find Q, A is always going to be 0, 0 for the sine function. If I can find Q, then I automatically find this by cutting it in half. Does that make sense? Okay. This point here and this point here. Okay, the blue points. Would you agree those y values are pretty easy to locate? Really easy to graph 1 and negative 1, right? How does the x coordinate of E relate to A and I? Halfway. Okay. How does the x value of M relate to I and Q? Same thing, halfway. Okay. So what we're going to do is we are going to, when we graph the sine function, well, that's pain, but we're only going to graph the red ones and the blue ones. Okay? And if we graph the red ones and the blue ones and draw a smooth curve, then we have our sine function, right? What I want to make sure that we understand, and this I get this every year, is that we do not do this. That purple stuff is not the sine function. Okay, sine function is smooth, not rigid. Does that make sense? Okay. So what I want to do real quick is just have you guys draw out a x and y axes. So when we graph the sine, cosine, secant, and cosecant, tangent and cotangent are a little bit different. We're going to draw an x and y axes, but we elongate the x-axis in the positive direction. We can draw, we could put our y-axis smack dab in the center if we want to, but generally you see just the first and fourth quadrants being elongated. Second and third quadrants we usually don't deal with too much. We can, but initially here just graphing the sine function is all I want to do. And what we're going to do right now is I'm going to restrict us to say, let's just do one period of y equals sine of t. Okay? We talked yesterday that a period of the sine function, which we call p, right now is 2 pi. Okay? We're going to change that eventually. It's actually 2 pi divided by the coefficient of t, when t is 1 here, so 2 pi divided by 1 is 2 pi. Okay? And we call eventually that coefficient of t, we call it b, but we'll get to that. I'm going to find 0, 0, and now everybody's graph is going to be a little bit different because you are going to define how big the period is. Okay? So I might go all the way out here and put 2 pi there. You might put 2 pi right there. Does that make sense? But regardless, because our x-axis is free to change as we see fit, as we are creating it, your scale might be different than my scale, but everything on yours, if you follow the same steps that I did, will keep your sine curve scaled appropriately for your dimensions. Does that make sense? Okay. So everybody's might look a little bit different. Just like if I told you to graph x squared, you might make your x-axis bigger than your neighbor's x-axis. You might make your y-axis bigger than your neighbor's. But what we're going to do, we're going to label our x-axis in terms of pi. Okay? So the reason I like doing this, I established 2 pi, and now does it make it really easy to find halfway? So go find halfway, and I've got pi. Is it then really easy to find halfway between 0 and pi? And then it's really easy to find the halfway point between pi and 2 pi. Okay, so if you cut your things in halves like that, no matter where you put 2 pi, your graph is going to be accurate here, even if it looks a little bit different, looks a little bit maybe stretched out or more compressed than what your neighbor's does or what mine does. Everything should be okay. Now the y value on the unit circle, because the unit circle, the y value never gets outside a range of -1 to 1. So my y value is here. I'm going to establish as 1 and -1. Okay, so when we graph these things, we're always going to graph the x-axis in terms of radians and the y-axis in terms of our integers. Okay, now our integers are still here. You know, that's 1.57. So I still have an integer of 1 right there if I wanted. Okay, I'm just not highlighting it. Does that make sense, everybody? Okay, and we might see, it just depends on the time, some questions that require us to be able to do that. But now what we're going to do, we're going to graph the sine function. So going off of those parent function points that we just mentioned, the 5 that are easy to graph, we know the sine function is always going to start at 0. And if it's got a period of 2 pi, that means it's going to end at the same spot that it started. So I put my starting and end points down first, right? What happened halfway in between? Yeah, had another x-intercept, right? Okay, so we'll always go through and plot our x-intercepts first. Okay, now remember that the sine function, the way we're generating this is that we were moving along the unit circle and capturing the y values off the unit circle. Well, when you moved off the unit circle, okay, you went counterclockwise first. You went into the first quadrant first, right? So your y value was positive first. So the sine function from here is also going to go positive. Does that make sense? Because of the way it came off of the unit circle. So at pi over 2, what's the y value for pi over 2? 1. So I plot that point. And now because of symmetry, I'm going to, as I construct my graph, and I come through that point there, come back down through pi, at 3 pi over 2, where am I going to be? -1. And those are your 5 points that you're going to connect with a smooth curve. I think it's easier, kind of like, instead of one continuous, I like to do a little sketching. Just easier for me. But that's a period between 0, 0, and 2 pi. Okay? If I want to go between 0 and 4 pi, all that you end up doing is extending your graph. Okay, I'll cut that distance 0 to 2 pi and paste it here. And I find the halfway point would be 3 pi. Halfway point here would be 5 pi over 2. This would be 7 pi over 2. Those are my x-intercepts. This thing reaches at 1. This thing here reaches at -1. And we could, essentially, basically what we say is we cut and paste, and we get another cycle or one more extra period of the sine curve. Does that make sense? Now, I can keep doing that, keep duplicating it all the way to 6 pi, 8 pi, whatever I want to go to. I can go to negative 2 pi, negative 4 pi. So basically, I can cut and paste and attach it or paste it to the left. Okay? So that's the sine function. Those are the parent points, the parent function points that we want to commit to memory so that we can establish a quick way to graph, because here's the end goal. The end goal is to say, okay, what do I get? How do I graph y equals negative 2 sine of 3t plus 5? Well, if you go back to chapter 4 in college algebra, we did transformations. That negative 2 is a vertical stretch. The negative is a reflection. That 3 is a horizontal compression, and the 5 is a vertical movement. Okay? If I could do that to each one of those parent function points, which are the easiest ones to do that to, we should be able to quickly graph negative 2 sine 3t plus 5. Okay? And we can also add or subtract something from that 3t to make it move left and right if we needed to. So that's kind of we're laying the groundwork to be able to get to that type of thing here in the next week or so. Okay? Tomorrow we'll come in, we'll graph that again, but then we'll start the cosine function, and then hopefully get into the secant and cosecant. If I know the sine and cosine, the secant and cosecant are the what of those things? They're careful, not the inverse, reciprocal. So if I have a y value of 1/2 for this curve right here, what's the reciprocal of that? It would be 2, right? Okay. If I have a y value of radical 3 over 2, the reciprocal of that is 2 divided by radical 3. Okay. If I have a y value of 1, the reciprocal of that is 1, right? So to find the cosecant, we'll just take these ordered pairs, these y values, and identify what the reciprocals are and plot those y values. And it'll give us the cosecant or the secant, depending on the function that we start with. So we'll do that tomorrow.